nanoHUB.org.
Online simulation and more for nanotechnology.
Hello, everyone. This is the first session where we will explore machine learning. The previous two sessions were about massaging data and organizing data such that you can do these kind of machine learning tasks. And in this session, we will explore supervised learning. We'll get our feet wet with linear regression, something that you might have done in Excel or MATLAB or your program of choice before, and then dive right into neural networks. So I hope it's exciting. So before I begin, let me briefly get us all on the same page in terms of why we are conducting these sessions and what is the role of this workshop. The central theme of data science and machine learning is learning from data. And you might have seen this in many different contexts in finance, marketing, from recommendation systems like Amazon and Netflix to your social media profiles. A lot of machine learning goes on behind the scenes. The applications in science and engineering continue to increase every single day. And there are many ways in which you can use these machine learning approaches in science and engineering. You can build machine learning models to act as predictive models, make predictions for continuous values. You can perform classification tasks, dividing images or objects into different categories. You can perform dimensionality reduction, where if you're working with high-dimensional data, it might be useful for you to use some kind of machine learning technique to bring down the search space into something that you can visualize and work with more easily. Perhaps most excitingly though, you can use these techniques in a design of experiments manner. So let's say you are in the lab conducting experiments to design the next best material for some property or the next best structure. You can guide these experiments using machine learning models where the model will guide you towards the next best experiment that you can perform such that your likelihood of success is maximized. Now, the goal of these sessions in general is to familiarize you with all of these approaches. And to do this, we need cyber infrastructure because the applicability of these techniques is limited by the cyber infrastructure, the codes, and the platforms available for you, the general user, to use these techniques. We will be using nanoHUB in conjunction with some other materials platforms as need be to explore these techniques. In this session specifically, we'll look at predictive models for continuous values, so regression tasks. And that is the general outline of this session. We'll start with linear regression, again, something you might have done many times in Excel or MATLAB or your program of choice. But then we'll jump into neural networks and do something more exciting. And in the second half of the session, I'll leave time for questions and answers. That way we can make sure that we follow along and make sure that we're all on the same page. So let's jump into it. The first thing that we will do is linear regression. And a common theme across machine learning approaches is that you have data at hand and you want to explore trends in data. You want to explore how some values are correlated with the other values. So let's pick an example here. And I'm sure there are many examples that you can come up with. This is one example that I have come up with from the materials field. Some of you may have seen this curve before. This is potential energy as a function of interatomic distance. This is a description of how atoms interact. So at large distances, atoms don't interact at all. And at very small distances, they feel repulsive forces. This is something you might have recalled from your undergraduate classes. The key features here are that the depth of this well, labeled E0 here, is a measure of how strong the bond is. So now if you think of something like melting, where you have a material that has to go from a solid ordered phase to a disordered liquid phase, you would imagine that you'll have to break quite a few of these bonds so that you can break the order and move into a disordered structure. So the stronger the bond, the harder it would be to break, and you would imagine that your melting temperature would be higher. Let's consider another property, stiffness of the material. Stiffness of the material is given by the curvature of this well. So this curvature here, the second derivative, and you would imagine that a higher bond strength, so a deeper well, would also be a steeper well because it would fall off very quickly. So a high bond strength would also result in a high stiffness. You can characterize stiffness in many ways. We'll use Young's modulus as an example, but the point being that both melting temperature and Young's modulus, quantities that you can measure in the lab, are correlated to the bonding strength in the same way. If you actually look at data of melting points and Young's modulus, you would expect them to have a positive correlation. As one increases, the other would increase as well. And that is, in some sense, our first foray into machine learning. We know this, we intuitively know that this data should be correlated. Can we explore that, and can we start fitting models to make predictions? The first model we'll make is linear regression, which means that we will try to predict the Young's modulus based only on the melting temperature. So the answer to the question, can we even do that? To answer that question, let's go to this link here. I'll ask all of you to go to nanohub.org/tools/MSCML and click on the launch tool button. This is where I jump into the hands-on demonstration part of the session. And if you feel like you're falling behind, please refer to the handouts and work at your own pace, or you can follow along with me as I do this live. So let's go to nanohub.org/tools/MSCML. This is a tool on nanoHUB that you can all run by clicking Launch Tool. And this is a Jupyter Notebook tool. I know some of you may be new to Python or Jupyter Notebooks because of your background. You have been maybe coding in MATLAB or C all your time, or maybe you are an experimentalist and you're looking to getting into this. So I'll spend a little bit of time getting into the basics of Jupyter Notebooks and Pythons, but I'll encourage you to watch the recordings for the previous sessions in order to get more in detail walkthrough of how these things work. For this session, let's jump right into the second notebook here, the second link called Linear Regression to Predict Material Properties. What I'll be doing here is walking you through some code and running it live, and you can run the code along with me or choose to do it at a later point based on your convenience. So this is a Jupyter Notebook. For those of you who haven't seen this before, it consists of cells, and the cells can be of two types. You can have cells that contain code or cells that don't contain code. The first cell here, as you can see, looks like plain text. This is a cell that doesn't contain code. The key thing that you need to know here is how to run a Jupyter Notebook, and you do that by running cells. And to run a cell, you can hit either the run button here or you can hit Shift Enter. I will prefer Shift Enter as it's easier for me. So let's get into the linear regression piece. We said that we would predict the Young's modulus of a material based on the melting temperature, right? And you can swap this out with whatever example you have in mind, maybe for your research. The first thing we need to do is get the data, explore the data, and then see how we can fit the model. So to do that, we will use two libraries called PyMatGen and Mendeley. We have been using these libraries in the previous sessions to get the data for the materials as well. We'll continue to do the same. Just for some of you who are new to Python, you might not have seen statements like these before. These are import statements, which allow you to import libraries in your code. Libraries are pre-packaged bundles of code that you can just import and use their features without having to write code yourself and run it yourself. So these are some libraries. We will use PyMatGen and Mendeley to get the properties of the materials. What properties do we want? We want Young's modulus and the melting temperature. To do the linear regression, you don't want to do it by hand. Remember, in Excel, you can do it in a few clicks, right? You want to do something similar here. You want to use someone else's work. So we will use the scikit-learn package. That's sklearn there, scikit-learn. It's a very common package, a popular package to get into machine learning, even linear regression. So highly encourage you to look it up if you're looking into getting into this area. Scikit-learn is a very good starting point. We will use the linear model class that contains a bunch of linear models, as you'd imagine, one of which being the simple linear regression, y = ax + b, which is what we'll use today. So here's a cell. Let's just hit Shift Enter. And I told you that this cell is going to query PyMatGen and Mendeley to get the data. That actually happens in this for loop here. Not a concern for this session in particular, but if you're curious about how this works, you can go back and look at this code in more detail, or look at some of the recordings for the previous sessions where we walk into this in great detail, including basic Python structures. All you need to know here is that we have these things called lists. It's basically like an array, except you can store multiple kinds of objects in lists. And we will build up these lists by querying PyMatGen and Mendeley for properties like Young's modulus, melting temperature, and so on, and just add those to the list. So if you see this number here, like 1, that means that the cell has completed execution and you can go on to the next cell. So let's do that. This cell prints the Young's modulus as it says here. You can see how these lists look by printing them. So this is how the Young's modulus lists look like. We have some numbers. Maybe if you want to print the melting temperature, you can print that list. So print is how you print in Python. There you go. This is the data for the melting point. So now that we have our data, we need to start building our model. But before that, a central theme of machine learning is dividing your data into training and testing sets. The reason to do this is something we'll get along in the later part of the session, but the point being that whatever model you build, be it a linear regression, be it a neural network, be it something more fancy, you want the model to learn the trends in the data and not overfit completely, not be too flexible such that it memorizes the data and doesn't learn the trend. We'll look at an example of this later, but the point is that you don't want models that memorize data but actually learn trends. And the way to do this is to divide your data into training and testing sets. What that accomplishes is that when you train the model on the training set, it gets as good as it can to learn what the right predictions should be, but then you can test it on some unseen data before, called the testing set, and then you can evaluate how good is your model when it sees something new for the first time. That is the concept of dividing data into training and testing sets. We will do that for all models, including this linear regression. So let's hit Shift-Enter to run these cells. This big block of code is where this division happens. It's really simple. Let's just run this cell and then we can look at what's happening. There you go. This cell has completed. So let's actually do some live coding. So this plus button here allows you to insert a cell. So I'll do that and I'll write some code. I said I divided the data into training and testing sets. I want to know how many data are in the training set and how many data is in the testing set. So we can do that. Remember, we said these are lists. So one way to find out the length of a list is to print the length of the list by using the function len for length. So the list for the training set is this value here, young_train. So let's print that. This value will print us the number of elements in that list, hence the number of elements in the training set. Let's also print the length of the list that contains the testing set. I believe it's called young_test. There it is. If you do that, you'll see you get two numbers here, 45 and 6. Remember, Shift-Enter to run the cell. So you see we have 45 elements in our training set and 6 elements in our testing set. That's like a 90-10 split, 90% training, 10% testing. That's typically what you would do, but you can feel free to do it 80-20 or any other split you like. That's the data. We said we'll split it into training and testing sets so that we can test how well the model performs on data it hasn't seen before. So let's actually make the model. Now, the reason we are doing linear regression, something that's easier to do in Excel in Python, is that the general flow of the process remains the same, be it linear regression or be it a neural network. And here's the general flow. To train models, you want to declare a model object first. And the way to do that is to use a line of code like this. So model equals linear model.linear regression. So what does this line of code do? So this line declares a model object. An object is basically a structure, a data structure that contains methods and variables inside of it. So you can use those properties of the object. In this case, this object is an instance of the linear regression class that comes from scikit-learn. This is a class from scikit-learn. So when we declare an object, it has all the methods of the linear regression class inside of it. One method is the model.fit method. So the .fit command is what trains the model. So we've declared a model object, and then we can say model.fit to train the model. Train the model. So what do we pass into the model.fit command? Well, if you're training the model, we want to pass in the training set. And because we're doing linear regression, we have a y-axis and an x-axis. So we just pass it that. So we pass it the X values for the training set and the Y values for the training set. That's it. This is all you need to train the model. Once you've trained the model, you want to make some predictions. And we'll do that using the model.predict command. So the .predict command is what you used to make predictions. But I want to make these predictions not just on my training set, but also on the testing set. So what we've done here is just join them, join the train and the test set, both for the X and the Y values using the NumPy concatenate feature. This is just one of the many ways to do it. All you need to know here is that we are just merging the training and testing sets so that we can make a prediction across all this set in one go, rather than having to call predict 2 times. Those are the predictions. And we'll also print some model information because we're doing a linear regression, we can print the equation, we can print some other metrics. That is our regression function here. Let's hit Shift Enter on that. Remember, this is just a function, so we've written this block of code that isn't actually executed yet. We'll call this function in just a second. But the point being that you declare a model object, use model.fit to train the model, and use model.predict to make predictions. So here's a function that plots the data, and this is useful because once you've created a model, you want to visualize how well the model is performing. We will use Plotly to make these plots, and the mechanics of the plotting are not a central focus of this session. If you're interested in Plotly and want to make really cool plots for your data, for your research, please have a look at the earlier sessions. Session 1, I believe, walked through Plotly in much more detail, even session 2 to some extent. But for now, let's just take this cell and run it. Trust me on this, that this makes a plot. You can see that this cell has completed execution as well. Here's where we'll actually call the regression function that we wrote. This is where we get to execute all those lines of code that said create model object, model.fit, model.predict, etc. And then we make the plot. So let's run this. You see, we print out the equation of the line, and we'll print out a plot in a second. So let's look at the equation that we have. It's a simple linear regression in 1D. So there's y equals ax plus b. We have a slope and an intercept, and it looks like our slope is 0.12 and the intercept is -85. Whatever, that's fine. We can also look at things like the R-squared error and things like that that you would typically associate with a linear regression. But most importantly, we can visualize this model in the space of our data. So it's a linear regression. So Young's modulus on the y-axis, melting temperature on the x-axis. We know from our intuition that the data should be correlated, which it is. There is a positive correlation. But you see that this linear model shown here in blue doesn't quite capture that. It's okay for small melting temperatures, but for many points over here, you see that the linear model isn't quite accurate enough. The question then arises, how do we improve this? And that is where neural networks come in. But at this point, I hope you're comfortable with the whole process of setting up a linear regression. You can go through these cells and run the other regressions as well, but let's spend a second and write down the outline of what we've done here. This is the outline for training any model in general, really. You want to declare a model object. We did that by saying model equals linear regression. And then you want to train the model. The way to do that is typically by a model.fit command. And then you want to make some predictions. That's going to be model.predict. I hope that's simple enough. We'll do the same thing for a neural network, exactly the same process. There'll just be more steps in between. I hope that's comfortable to you. So let's jump right back into the PowerPoint here. We've seen how the linear regression performs. It's a decent fit, but I think we can do better. One way to do this is to think about what other data that we have on our hand. We queried the database for Young's modulus and melting temperature. But at the same time, we also know things like atomic mass. We know things like electronegativity. Would that help us make a better prediction? That is essentially our question that we're trying to answer with neural networks. But before we do that, we need to have a brief understanding, a crash course-like understanding of what neural networks do. A neural network shown on the right here tries to mimic the structure of the networks of neurons that are actually present in your brain. The key abstraction here is that a neuron, shown by these circles here, is abstracted as an entity that takes in inputs, performs computations, and computes some outputs that it then passes it along to the next neuron. Okay? So consider this network here. We saw how training for the Young's modulus with just the melting temperature as an input isn't quite good enough. The linear regression wasn't quite good. So maybe we'll throw in one more quantity, the electrical resistivity. And let's call them Tm and rho. Can we use these two quantities to make a prediction for the Young's modulus? So here's a simple neural network. One thing that we do when we make these networks is that we organize nodes or neurons in layers. So here's one layer, which is the input layer. This consists of neurons that are part of our input, so melting temperature, resistivity. We have the output layer, which is the quantity that you want to predict, in this case, the Young's modulus. In between, you can have however many hidden layers you want with however many nodes or neurons that you need. You might have heard of phrases like deep learning, which typically consists of 15 to 18 hidden layers. So it's a gigantic network. Here we have just one hidden layer because this is a demonstration. In the code, we'll see about 3 hidden layers. So let's walk through this. What does this neural network compute? Well, it's a collection of weights and biases. So let's focus on the neuron A1 here. Let's say we wanted to calculate the value of A1. We see that it has 2 inputs, melting temperature and resistivity, and the weights are W1 and W2. So the first thing we'll do is call A1, which is sometimes called the activation value of that neuron. We'll call it as W1 times Tm plus W2 times the resistivity, rho, plus a bias term B1. Okay, so that's the basic part. You have weights times inputs plus a bias. Now, if we stop here, we would notice that it's just a linear combination of the inputs. So how do I predict, how do I match some nonlinearity? What if my function is quadratic? This is where an activation function comes in, shown here as f1. We'll look at this in a second, but the role of the activation function is to look at nonlinearities and help the neural networks predict nonlinearities better. That's the value of the neuron A1. If we wanted to do the same for A2, we would look at the inputs, the weights, and the biases and write down basically a similar equation. A2 is W3 times Tm plus W4 times rho plus a bias B2 and an activation function applied to it. You can do the same thing for the Young's modulus. The inputs for the Young's modulus are the nodes A1 and A2. So you have W5 times A1, W6 times A2, and a bias B3. The activation function gets applied later. And this is it. This is the prediction of your model. So let's look at these activation functions. You can have the simplest activation function you can have is do nothing, which is a linear function. So it's just going to take in the input and spit out the same output. Common activation functions are hyperbolic tangent, tanh, sigmoid, and ReLU, called rectified linear unit, which is what we will use in our code in a second. The job of this nonlinear activation function is to snub out the input if the input is less than 0, but maintain f of x equals x if the input is positive. That is generally how the feed-forward structure of the neural network works. So we said that it's a collection of weights and biases. How do we know that we have the right weights and biases to make a decent prediction for the Young's modulus? What if I start out with random weights? It's not guaranteed that I'm going to get a good prediction. This is where you need to describe the process that allows you to train the network. So one thing that you can do is define an error metric for your model. So in this case, we will use mean absolute error, and you can also use mean square error, which is a method for your model to know how far it is away from the ground truth. So if your ground truth is a prediction of 100 GPA for the modulus, and you predict 0 GPA, then your model is pretty bad. But if your model predicts 95 GPA, you're pretty close. So you need a metric to measure that. And given this metric, you need a way for your model to go from random weights and biases to the weights and biases that will minimize or maximize this objective function, achieve decent predictions. The way to do that is via backpropagation, which is where you describe a scheme that updates your weights sequentially and drives them towards the right weight values. Similar to any optimization problems, if you're familiar with optimization techniques, that's basically what's happening here, except that the deep networks and more common networks that you'll see in the wild, the optimization is going to be very high dimensional because you can have many neurons or many layers. But the concept is the same. So with that being said, let's jump into the code here. So I want everyone to go back to this landing page here. Again, it's nanohub.org/tools/mscml. But I already have it open here, so I'm just going to pull it up. I want everyone to look at the third notebook, which is neural network regression. Again, this is the same style of a Jupyter notebook, contains code cells and markdown cells. Let's hit Shift Enter. We're down to our first code cell here. Again, we'll use PyMatGen and Mendeley to get properties like not just the Young's modulus and melting temperature, but other properties that you imagine you would know, like lattice constants, atomic numbers, ionic radii, etc. So that's happening with PyMatGen and Mendeley. The other library that we'll use is Keras. So Keras is an API built on top of TensorFlow here that comes from Google. You might have heard of other deep learning libraries like PyTorch that comes from Facebook. The functions are essentially similar. We will use Keras here. Let's go ahead and hit Shift Enter on this cell. It will take a while. The first thing that we will do is, again, the same thing, get all the data and organize it. And again, the details of this are a story for another time. But in the linear regression case, we obtain the Young's modulus and the melting temperature. Here, it's going to be many more properties like that. And to handle these wide variety of properties, we will structure it in a pandas data frame. Let's run this cell here. Pandas data frames essentially give you the look and feel of Excel in a Jupyter notebook, but give you the power, the processing power that most Python objects would have, like slicing and filtering. Here's, for example, a short snippet of our data frame. The first row consists of atomic number 47, which I think is silver, boiling points, electronegativities, lots of other things. So now that we have our data, the next thing that we need to do is divide our data into training and testing sets. Let's do that. But let's focus on one extra aspect as well. If we look at our data closely here, we have data that span many ranges of values. Electrical resistivity is of the order of 10 to the power minus 8. Boiling points are of the order of few thousand Kelvin. These numbers are of very different scales and, of course, depend on the units that you choose those numbers to be in. So if I choose distances to be in meters versus picometers, my numbers are going to drastically change. How do I account for this? How do I make sure that the model does not get caught up in the units? One way to do that is to normalize your data. And there are many ways you can normalize it. You can normalize it such that the maximum value is +1 and the minimum value is -1, or you can do 0 and 1. The way that we will do normalization is called standard score normalization. You might have seen this from some statistics classes. You take the data, subtract the mean, and divide the standard deviation. So let's hit Shift Enter on these two cells here. So the normalization happens in this piece. The np.mean command takes the mean of your data. The np.std command takes the standard deviation. So you take your data, subtract the mean, and divide by the standard deviation. And you see that now if you print some of the data, you've gotten rid of all the 10 to the power minus 8s and the thousands. Now the data is roughly in the range of -2 to 2, which is what you want. Now that that is done, let's create the model. So here's the model, and this is essentially the crux of this session. How do you create a neural network? The process is the same. You declare a model object. The only difference being that the model object is now an instance of the sequential class. The sequential class is a class from the Keras API that allows you to declare models, and it internally makes the connections between the nodes for you. So you don't have to take care of all those details. So we have our input data. So we need to pass it into the network. And once we have a network, we can have however many hidden layers that we want. So here's the structure to add a layer to a network. You want to use the model.add command to add a layer to your model. You want to add a dense layer. A dense layer is the simplest kind of layer that you can add. It takes care of all the connections behind the scenes such that each neuron in your new hidden layer is connected to each neuron in the previous layer. The next number that you put in is the number of neurons. I can do 32 neurons. If you want to do 100 neurons, go for it. Let's go for 32 neurons. The activation function that we saw for the nonlinearity is specified by the keyword activation. And you can say ReLU, you can say tanh, you can say whatever you want. There are two other parameters here. This is really the minimum that you need to describe a layer, but there are a few other things. If this is the first hidden layer that you're specifying, like this one here is, you need to specify that this is the first hidden layer. And the way you do that is by saying that this should be connected to the input data. And the way you do that is by passing a quantity called input shape, which tells the model, which tells Keras, how many inputs am I expecting? So in this case, if we have around 30 inputs, the value for input shape is going to be around 30. So this tells us, just for this first hidden layer, that we are connected to the input neurons. Subsequently, we don't need to specify that because it's a hidden layer and it's a dense hidden layer, which means that Keras knows that this second hidden layer is connected to this first one here. So that is obvious, but the first layer, you need to specify input shape. And this, so we have our first hidden layer, our second hidden layer, and I know that this is the output layer. How do I know that? Because this is a dense layer with only one neuron, which is the Young's modulus, right? That's the quantity that we want to predict. So this is all you need to specify a neural network. This is the broad structure. There are a few other things that you need to know. We said that we will initialize our weights and biases randomly. The default initialization is random, but if you want to control that for some instance, you can specify it with the kernel initializer command. So this command sets the weights and biases, well, really the weights, to the values which you want it to be. You can specify this as random, or you can start with all zeros. It's recommended that you start with random weights. Now that we've specified a structure, we need to know how to train the model. So we need to specify a metric, how good the model is, which is called a loss function. We saw mean squared error. The one that we'll use is MAE, which stands for mean absolute error. Same thing, take the prediction from the model and subtract it from the ground truth data, take the absolute value of that. And the model.compile command is where you can specify the loss function and the optimizer. The job of the optimizer is to specify the process, the training process by which you will achieve the right weights and biases. In this case, we will use an RMS prop optimizer. There are many other options, and it's a story for another time. But the optimizer is what takes care of taking the weights from random values to values that will give you good predictions. Let's run this cell. You'll see this table here. This comes from the model.summary command. So this summarizes the model for you. And this is a useful debugging tool because if you wanted 3 hidden layers and you wrote your code and you run the cell, and if the model.summary tells you you have 2 layers, that something's going wrong. In this case, we wanted to specify 3 layers, so that is what we have. We have around 2,700 parameters. So let's go ahead and train the model now. We've declared the model object. There's a few extra steps in terms of adding layers, but we've taken care of all of that. Let's actually train this cell here. So again, it's the model.fit command. You pass it the training data, which is the inputs to the model, the atomic properties, Young's melting temperature, etc., and the labels, which is the Young's modulus. While this model trains, let's focus on one other aspect of this model.fit command, which is the validation split. We said that we will divide our training data into training and testing sets so that the testing set is untouched and we can see how the model performs on unseen data. So while we're training the model on our training set, how do I know when to stop? How do I know this model is trained well enough? Well, if you train the model for as long as you feel like it, you run the risk of overfitting the model. What does that mean? The problem is that the longer you train the model, the more it will memorize the structure in your data rather than learning the trend. So let's say you have a quadratic curve. A straight line isn't going to fit that data. A quadratic function will fit the data, but if you train the model for long enough, because you have thousands of parameters in each neural network, it can learn a 15th degree polynomial that will also fit your data very well. But it isn't quite the solution you're looking for because it's memorized the data, not the trend. One way to stop that happening is by using a validation set. So we've already divided our data into training and testing sets. Within the training set, we can keep 10% as a validation set. And as we train the model, we will look at our validation set. Is the model still doing well for the validation set? And if yes, keep training. And check again, keep training, check again, keep training. And the moment the error in the validation set becomes high, that means the model is trained so much that it doesn't know how to perform for a validation set, you stop the training right there, because anything longer than that means that your model is overfitting. So this is typically a kind of loss curve that you will see, mean absolute error as a function of iterations or epochs. They're subtly different, but we'll get to that if you have questions. The blue curve is the loss on the training set, the error. As you would expect, if you start from random weights, it's going to be a very high error, and then it goes down. And the error on the validation set also goes down, and we've stopped it much before it starts increasing again. One thing that you can do is save your Keras model. If you've trained a deep network with 20 layers and many neurons, it might be time taking for you to train the model again and again. So you can use the model.save command to save this model, and you can load it and make predictions on the fly again and again. To test the model, we can use the model.evaluate command. So this is what tests the model on the unseen testing set, right? You always want to train on the training set and test on the testing set. And you see that the error is 28 GPA, the mean absolute error. So what does this mean? We can look at that in a plot. So let's go ahead to the plotting piece here. Again, it's plotting. If you're interested in that, look at the previous sessions. But here's the plot that we're making. We're making the predicted value from the neural network on the y-axis and the real value, so the ground truth data on the x-axis. And you see that the data is aligned along the y equals x line, the match line, so much better. The predictions are quite close to the ground truth data, even for the training set in blue or for the testing set in red. There are a few points that are off, but this neural network does a much better job than the linear regression at predicting the Young's modulus. And that's it. That is all you need to do to train a neural network. Let's recap a little bit here. The outline is the same. Declare a model object, right? We always start there. In this case, it's a sequential object. We can then use the model.fit command to train the model, and we can use the model.evaluate or the model.predict command to make predictions or evaluate the model on a testing set. The only addition here is that declaring a model object involves a few more steps. We use the model.add command to add layers. We can add however many layers we want. And that's it. That is all it took to train the neural network. So this is basically the key punchline here, right? We saw a linear regression with two parameters, a slope and an intercept. We saw that it can't really make decent predictions for across all the training and the testing sets, but the neural network with thousands of parameters is much more flexible, so it can perform a much better fit to the data. So let's jump back to our big picture here. We saw a little bit how the models like linear regression and neural network can help us learn from data. That was the focus of today's session. If you feel that you want to train neural networks for your research, for your data, for whatever, maybe you have some other interesting applications in mind, I would encourage you to visit the tool that we demoed today, nanohub.org/tools/mscml. Use that maybe as starter codes and work in either the Jupyter environment or nanoHUB, which allows all the libraries to be pre-installed, so you don't have to worry about that, or work with those codes in your own environment of choice and get started there. So hopefully that was enough of a push for you to get started. I will stop talking now and allow questions and answers. That's it. Thank you.
All right. Thank you, Saaketh. Let's all join in thanking him by, I guess, applauding over WebEx. So I guess unmute yourselves, and then we can get to the Q&A. So if there's any questions, you may ask them now, or if not, I can start off the question and answer session. I'll give it a couple seconds.
I have a question for Saaketh. First, thank you so much for the tutorial. It was really good. I would like to know if it is possible to do or multi-output neural network. We can build a neural network with different outputs.
Absolutely, yes. You can definitely do that. There are many examples where you would be interested in predicting multiple outputs. You do have to take care of, again, things like units and making sure that the data is in roughly the same range, but absolutely, yes.
In that case, is it possible to train just one model, or do I have to train multiple independent models for each output?
You can do either. There are examples of both. There are examples where people train models for multiple outputs. Classification is one common example where you need multiple outputs. You need to classify an object into different categories. That's an option. But there are instances where you would imagine that one network may not be complex enough of handling two different outputs, in which case you can use two different models. I would say it's still with a deep enough network with enough number of neurons, you should be able to get away with having just one model for how many ever outputs that you want. But there are examples of both. So feel free to do it however you like it.
Thank you.
All right, seems that we have a question in the chat. So the question is there any limitation for the number of input parameters that the neural network can handle?
So is this in terms of the number of, I'm assuming this is the number of inputs that the model can handle? No, not really. Because if you, for example, you can have, there are many approaches to this, but one of the models that you can have read in an image and make some predictions. This image can be 1,000 by 1,000 pixels, which means that you have 1,000,000 inputs to your neural network. It is large, it's a very deep network, and the training is going to take a lot of time. But no, theoretically, there's no limit in terms of the number of inputs. Of course, as you increase the number of inputs, you will need more and more nodes in the hidden layer so that you can handle all these inputs and learn from all of these inputs. Imagine if you have 1,000,000 inputs to your neural network, but you only have 2 neurons in the hidden layer. It's going to have a hard time combining the information from 1,000,000 nodes into 2 neurons. So the more inputs you have, typically the more neurons you'll need in the hidden layers, but there's no limit. You can absolutely knock yourself out and go crazy on the number of neurons.
So hopefully that answered your question. Are there any other questions for Saaketh?
Excuse me, I have a question. So how do you decide how many epochs you use to train the model? And also, you have the real-time epoch real-time counter class. Can you explain that as well?
So I'll answer the first part of the question first. How many epochs do you train your model? In this demonstration, I trained it for 2,000 epochs, but this is where the role of the whole validation set comes in, right? You don't want to pre-decide that I want to train for 500 epochs because that might be too less or too much, and you don't have a way of looking at that and knowing. The way to do that, one of the preferred ways to do that is to use a validation set. So you have your training data that you're using to train your model. Within that training data, you split it into a training and a validation set. You train on the training data, and every time you update the weights, you check the validation set. Is the model still doing okay on something it hasn't seen? If yes, then keep continuing. And you use the validation set as a stopping criteria. So in Keras, you have a feature called early stopping, or you have the feature of adding stopping criteria, which will depend on your validation set. So what you'll do is you'll say, not train for 500 epochs, but you'll say, train as long as the error in the validation set is lower than this much. And it'll keep training however long it needs to. That is the preferred way of doing that. That way, you don't manually stop it at a point that you feel might be okay, but might actually not be enough for the neural network, or might be too much. So I think someone has put a link to the early stopping Keras page in the chat box, but that is typically a criteria that you want to use. It's similar to the optimization problems. You typically have optimizations not for number of iterations, but for a criteria. You typically always check a criteria, convergence criteria, or something like that. This is the same here. You check the criteria on the validation set. Can you repeat the second part of your question once again? I didn't catch that fully.
Can you explain the epoch real-time counter class in your Jupyter notebook?
Let me go back to the notebook here. Looking at this plot here.
Yeah, I think it's the block above this.
She wants you to talk about the block of data that kind of plots that, I believe.
Oh, sure, absolutely. It's a very simple plot here. It is.
No, it's not this one. It can go above above the epochs equal to 2000.
Above the epochs, you mean this one?
No, in the code. So here is the epoch real-time counter class print epoch number. Yeah.
So this is yeah, absolutely. So this is the class that allows for this kind of a ticker to show up. Remember, when we were training this model, this thing kind of updated live. The way that does that is that when you use the model.fit command, you can pass in a callback. These are extra objects that Keras can evaluate while training. The object that we have passed is an instance of this class print epoch number, which basically flushes the standard output and prints the epoch and the loss. So all this callback does is that when you're training the model, as each epoch completes, it calls this print epoch number instance, and that in turn runs this code, and that's how you see this print here. You can use whatever callbacks you want. We've defined one here because it looks nice. You can do any other callback that you want. I hope that answers your question.
Okay, thank you. So in this training, you just define that you want to train 2000 epochs, right?
Yes, just for demonstration, and also because 2000 is just about enough time so that you don't have to wait forever. Because it might turn out if you have a lot of data and you're using a validation set, you might have to train a very long time. It depends on your data. So this is just demonstration.
Okay, thank you.
We have one more question in the chat. I guess if you would like to read it off and answer it.
Can you read it for me, please?
Yep. In the example, there were two variables in the input layer. What about the number of variables limitations for the neural network? That's the first part.
Okay, so is this? So there was a similar question to this before in terms of number of inputs that a neural network can handle, and there's no really limitations there. Is that the question, or is it about how many neurons do you want to use in the hidden layers? Feel free to unmute yourself and ask the question directly in case you feel that's more comfortable.
Private message. Okay, I guess I'll just go to the second part of the question. Does the computational cost depend on the number of variables in the input layer? I guess address that.
Okay, so I'll bundle both of these questions together. So just to reiterate, we saw in the slides a 2-neuron example because it's easy to walk through and write down the equations. If you have hundreds of neurons, you don't want to do that. In our neural network, we used, I forget, we have 16 inputs to the neural network, and our hidden layers have 32 and 64 neurons. So that's what we are using here. There is no limitation on any of this. You can go as big as you want, as deep as you want. The central concept of deep learning is to use 15 to 18 layers at least to make sure that you get all the features that you need. So there's no limitations there. That's one part. The second part of the question was about computational cost. Yes, the computational cost will increase because the more neurons that you have, the more weights you will have, right? So we added 2 hidden layers and we have 2,700 parameters. So the model needs to optimize all of these. If you have 15 layers, you will very quickly have millions of parameters. And to optimize all of that requires computing many more gradients, doing a lot of matrix multiplications. So yes, the computational cost will increase. I don't really have an order of n squared or anything like that off the top of my head, but yes, the cost will definitely increase as the number of parameters increases. I hope that answers your question.
I have a question. So if you go to the epoch thing, if you scroll down.
Scroll down.
The plot where you were showing the validation, yeah, this one. So you said here you had 2000 because of time limitations, but you can have callbacks to check when it starts to rise. Is that right?
Yes. Yes.
So my question is, how do you know, like if the rise is like a wiggly thing, like in the beginning around say 125 or 100, you also have a rise. So if you just check that it's rising and you stop it, you are not really stopping at the right point. So how do you ensure that it's not a local thing and it's the final rise that you're looking at?
Yeah, that's a great question. That's a great question. So the way to do that is, so I'll just comment it out here. So we saw the callback for the epoch printer. We have a callback for early stopping, which is where you would specify all these details. So you can say two kinds of things. Stop when the error on the validation set is less than some criteria, let's say 10 power minus 5, some criteria. That's one way to do it. But another thing you can specify is something called patience, where you can tell the model, if you see that the validation error is more than that, don't stop immediately, wait for maybe 10 epochs or maybe wait for 100 epochs, and then see if you still continue to be above that. That way, it allows you to get rid of blips like this. If I specify, let's say, a patience of 100, the validation loss would start here, but I would wait for 100 more epochs to see if that was just an artificial spike or is that really a trend. And then that can allow you to control that.
Thanks, that answers my question.
Are there any other questions at the moment? All right, I guess I'll ask my questions now. So it seems that you went through a couple of libraries hinting at Keras as one of them, and even a little bit on scikit-learn. And there are other libraries that are out there specifically for Python that are more common, such as TensorFlow, people might have heard of, or even PyTorch in some classes. So could you kind of address maybe those that you might feel beginners might start out with, or those that are more complicated, and I guess in your own personal opinion, can you kind of attest to the different libraries maybe?
Yeah, so scikit-learn is very popular because it requires the least number of lines of code for you to train models, in my experience. So it's very popular, but it also obviously gives you limited flexibility. But if you are completely new to this, feel free to go to scikit-learn, use their 2 or 3 lines of code, and you'll be done. Keras is also nice because you can do the same thing in a few more lines of code. It wasn't really difficult. It was model, declare model object, model.fit, model.evaluate. PyTorch involves more lines of code, but it's more flexible. So if you're a little bit of a not a beginner, but more like an intermediate Python level, and you're familiar with some object-oriented programming, then PyTorch is maybe more up your street because it involves defining classes and doing all that. Keras is much more simple to begin with. TensorFlow is the backend for Keras. So if you feel that at some point Keras is not enough for you, you need more fine-grained control, maybe you want to jump into TensorFlow then. But between Keras and TensorFlow, the transition is kind of seamless, so you can always flip back and forth. So my recommendation is, if you're an absolute beginner, scikit-learn. If not, jump into Keras, and then maybe you can progress to PyTorch or something else. There might be other libraries that I'm not aware of that are maybe much easier, but in my experience, this is generally the progression.
Thank you for that. So we have a couple more minutes. Are there any other questions that people might want to ask related to this, or even maybe even the first notebook?
And I can jump in and say, if there are any questions that you, for example, you're working with data and you want to train some of these models, but you're not willing to bring up questions in a public forum, you can always contact us separately and we can arrange how to answer those questions. But my key recommendation is to, at least if you're completely new to this, use these codes as starter codes and change them however you like for your purpose. If you are more comfortable with Python, I would encourage you to use the environments on nanoHUB where we have all the libraries installed. So you can use this as a playground, quickly test the things that you want to do, see if the idea even works, and then you can continue working on nanoHUB or shift to your platform of choice and work there. That's my broad recommendation.
Well, I guess if there aren't any more questions, please everyone unmute yourselves and thank the speaker one more time before we close this session.